In the architecture of the cosmos, empirical data serves as our singular, unforgiving compass. We construct elaborate mathematical frameworks to understand the genesis of the universe, trusting that our instruments will eventually validate our equations. But what happens when the telemetry returned by the most sophisticated optical instrument in human history fundamentally contradicts the established laws of astrophysics? In July of 2022, the James Webb Space Telescope initiated its primary scientific operations, peering deeper into the cosmic dawn than any apparatus before it. Its massive 6.5-meter primary mirror, comprised of 18 gold-coated beryllium segments, was meticulously calibrated for one specific purpose: to capture the ancient, stretched infrared photons from the very edge of observable time. The cosmological redshift dictates that, as the universe expands, the wavelength of light traversing it elongates, shifting from the visible spectrum into the deep infrared. The Hubble Space Telescope, a marvel of the 20th century, was fundamentally blind to this ancient light. Webb, however, was engineered to see it. And in its inaugural deep-field telemetry, astronomers did not find the slow, irregular accumulation of primordial matter they had theorized. Instead, they found an impossibility. Scattered across the digital canvas, residing in an epoch merely 500 million to 1 billion years after the Big Bang, were tiny, blindingly bright, unmistakably red anomalies. Hundreds of them. And as the analytical pipelines processed more data over the subsequent years, those hundreds multiplied into the thousands. They were ubiquitous, appearing in nearly every patch of the ancient universe we observed, representing roughly 1% of all galaxies at those extreme redshifts. In the formal literature, these anomalies were designated as broadline H-alpha emitters, a clinical term reflecting a specific feature in their spectral signature. But the astrophysical community, grappling with their sheer abundance and strange morphology, adopted a simpler moniker proposed by astronomer Jorrit Matthey, the Little Red Dots. To comprehend the magnitude of the problem these dots present, we must look at the timeline of cosmic evolution. Following the recombination era, roughly 380,000 years after the Big Bang, the universe transitioned from an opaque plasma into a transparent expanse of neutral hydrogen. This initiated the cosmic dark ages, a period devoid of stellar illumination. It was not until 200 million years later that gravitational perturbations caused the first hydrogen clouds to collapse, igniting the first stars and initiating the era of structural assembly. By the time we reach the 500 million year mark, the epoch where the little red dots reside, galaxies should be in their absolute infancy. Our standard cosmological models dictate that these early galaxies must be diffuse, asymmetrical, and slowly accumulating mass through a protracted series of gravitational mergers. They should look like chaotic construction sites. The little red dots, however, present a morphology of impossible maturity. They are hypercompact, fiercely luminous, and harbor stellar masses mathematically equivalent to our own Milky Way. Our galaxy required over 13 billion years of stellar nucleosynthesis and galactic cannibalism to achieve its current mass. Finding an equivalent mass concentration in an object barely 500 million years old fractures the foundational models of galactic formation. Observers at Penn State aptly labeled them universe breakers. Faced with a population of objects that defy standard categorization, the scientific method demands that we first attempt to reconcile the anomaly using known physical mechanisms. The initial hypothesis posited that the little red dots were starburst galaxies. This classification describes a localized region undergoing an explosive rate of star formation, often triggered by galactic collisions. In a starburst phase, immense gravitational compression forces raw hydrogen gas to ignite, producing thousands of massive short-lived stars. These stellar giants rapidly exhaust their nuclear fuel, dying in spectacular supernovae that eject heavy elements like carbon and silicon into the surrounding medium. These elements condense into microscopic dust grains, which act as a cosmic filter. They absorb the high-energy blue and ultraviolet photons emitted by the young stars and thermally re-radiate that energy in the red and infrared spectrum. On a theoretical level, the starburst model appeared to satisfy the observational criteria. It accounted for the extreme brightness, the compactness of the stellar nursery, the distinct red hue, and the presence of a strong Balmer break, a sharp drop in the spectrum at precisely 364.6 nanometers, indicating a massive volume of hydrogen gas absorbing photons. For nearly 18 months, the astrophysical community tentatively accepted this paradigm. Then, the mathematical scaffolding collapsed. In late 2024, astrophysicist Caitlin Casey and her team at the University of Texas at Austin subjected the starburst hypothesis to a rigorous quantitative test. In galactic mechanics, there is a well-documented, invariant correlation between the mass of a stellar population and the mass of the dust it produces. You cannot generate the sheer luminosity of a Milky Way-sized starburst event without generating a proportionally massive volume of thermal dust. When dust absorbs stellar radiation, it heats up, and that thermal energy must be radiated away in the far infrared spectrum. Casey's team utilized Webb's mid-infrared instrument, alongside ground-based radio observatories, to hunt for this specific thermal signature. The results were not merely anomalous. They were devastating to the hypothesis. The far infrared emission was virtually non-existent. The calculations revealed a dust deficit of 2 orders of magnitude. Less than 1% of the required thermal mass was present. To maintain the starburst hypothesis in the face of this data would require rewriting the fundamental laws of thermodynamics and stellar evolution. Furthermore, to generate the observed luminosity purely through stellar fusion within such a microscopic spatial volume, the stars would have to be packed so densely that their gravitational interactions would trigger catastrophic orbital decay. The system would tear itself apart in a fraction of the time required to produce the stable light signature we observe. The starburst model was fundamentally falsified. The collapse of the stellar hypothesis left astrophysics with exactly one known mechanism capable of generating such immense, sustained luminosity from a hypercompact region: a supermassive black hole actively feeding on an accretion disk. When a central singularity pulls in surrounding matter, the gas spirals inward at relativistic speeds. The sheer friction and gravitational compression heat the accretion disk to millions of degrees, causing it to outshine the entire host galaxy. These active galactic nuclei, or quasars, are well-documented phenomena. The little red dots exhibited broad emission lines in their spectra, a distinct kinetic fingerprint indicating hydrogen gas whipping around a central gravitational anchor at velocities exceeding 3.2 million kilometers per hour. Only the extreme space-time curvature of a supermassive black hole can accelerate matter to those speeds. But just as the active galactic nucleus theory gained traction, the telemetry introduced 2 lethal contradictions. First, actively feeding black holes are the most efficient X-ray engines in the universe. The superheated plasma in the inner accretion disk generates a torrent of high-energy X-ray radiation. Yet, when astronomers directed the Chandra X-ray Observatory and the XMM Newton satellite toward the coordinates of the little red dots, the sensors registered absolute silence. The X-ray emission was completely absent. Second, the mass calculations shattered a foundational law of galactic dynamics known as the Magorian relation. Formalized in the 1990s by John Magorian, this mathematical law states that a central supermassive black hole always accounts for approximately 0.1% of its host galaxy's total stellar mass. They evolve in a locked, symbiotic ratio. But when the kinetic equations were applied to the broad emission lines of the little red dots, the resulting black holes were monstrous. They accounted for 10%, and in some extreme cases, nearly 100% of the total mass of the system. The black holes were 1,000 times too massive for their environments. As astrophysicist Fabio Pacucci noted, the data presented an inescapable paradox. If they are black holes, they are impossibly large. If they are stars, they are impossibly dense. The tipping point in this cosmological crisis arrived via the Ruby Survey, the Red Unknown's Bright Infrared Extragalactic Survey, led by Anna de Graaf at the Max Planck Institute for Astronomy. Utilizing 60 hours of dedicated Webb observation time, her team captured the highest resolution spectroscopic data of these anomalies to date. In July of 2024, they isolated an object designated RU-154183, residing at a redshift of 3.548, meaning its light had been traveling for nearly 12 billion years. The team simply called it the Cliff. Its spectral signature was the most extreme manifestation of the little red dot phenomenon ever recorded. The V-shaped spectrum was razor-sharp, the Balmer break was nearly vertical, the broad emission lines were violently pronounced, and the X-ray signature was completely dead. The cliff proved that the little red dots were not slightly unusual galaxies or slightly obscured quasars. They belonged to an entirely separate, previously undocumented class of celestial object. To explain the cliff, the scientific community was forced to excavate a theoretical paper published 16 years earlier, long before Webb was even fully assembled. In 2008, theoretical astrophysicists Mitchell Begelman, Elena Rossi, and Philip Armitage proposed a radical solution to a different problem: how supermassive black holes could grow so massive so quickly in the early universe. The standard model of a stellar mass black hole slowly feeding over billions of years could not account for the billion solar mass behemoths we see at high redshifts. Begelman and his colleagues proposed a transient, monstrous phase of stellar evolution, the quasi-star, or the black hole star. Imagine a primordial hydrogen cloud so massive that it collapses directly into a small central black hole, but crucially, the outer envelope of the cloud does not disperse. It remains gravitationally bound. The black hole begins to aggressively devour the envelope from the inside out. In a standard black hole, the rate of consumption is bottlenecked by the Eddington limit, the point where the outward radiation pressure from the accretion disk equals the inward pull of gravity, blowing away the food source. But in a quasi-star, the hydrogen envelope is so vast and dense that it absorbs the immense radiation pressure. The envelope inflates like a grotesque, glowing balloon, hydrostatically supported by the annihilation occurring at its core. From the outside, this object mimics a star. It possesses a photosphere governed by the same thermodynamic limits as a red supergiant, burning at roughly 4,000 Kelvin, which perfectly explains the distinct red color and the massive Balmer break. But its engine is not nuclear fusion. Its engine is gravitational accretion. This elegant, terrifying model instantly resolves every contradiction in the Webb data. Why are there no X-rays? Because the high-energy radiation, generated by the central singularity, cannot penetrate the sheer density of the primordial hydrogen envelope. The X-rays are absorbed internally, superheating the gas, which then thermally re-radiates the energy as softer, optical, and infrared light. Why did the mass calculations violate the Magorian relation? Because the broad emission lines we measured were not solely caused by orbital velocity. As photons fight their way out of the dense hydrogen envelope, they undergo continuous scattering, a process that physically stretches their wavelength. When physicists recalibrated the equations to account for this violent internal photon scattering, the implied mass of the black holes dropped by orders of magnitude. The Magorian relation was never broken. Our mathematical models were simply unequipped to measure a singularity hiding inside a stellar cocoon. We are witnessing a ghost in the cosmic machine, a transient, highly unstable phase of evolution where a singularity incubates within a massive, stellar womb, gorging itself at rates that defy standard physics, before eventually detonating its host envelope to reveal the naked quasar beneath. If these quasi-stars are the missing incubators of the universe's most massive black holes, we are forced to ask what catastrophic mechanism could have planted these gravitational seeds in the dark ages of the cosmos, long before the first true stars ever had the chance to ignite. The standard cosmological framework dictates that the first generation of stars, population 3 stars, formed from pristine clouds of primordial hydrogen and helium roughly 200 million years after the Big Bang. These stellar bodies were theoretically massive, hyperluminous, and exceptionally short-lived, inevitably exhausting their nuclear fuel and collapsing into stellar mass black holes, singularities perhaps 10 to 100 times the mass of our Sun. However, mathematical models tracking the evolutionary growth of these initial seeds immediately encounter a hard physical boundary when attempting to reconcile them with early universe observations. If a 50 solar mass black hole is placed within a dense gas cloud at redshift 15 and permitted to feed continuously at maximum theoretical efficiency, the equations governing its mass accumulation fail spectacularly to produce the billion solar mass behemoths we now routinely observe at redshift 6. The timeline is mathematically prohibitive. The universe simply was not old enough for a stellar mass seed to accrete that volume of matter. The bottleneck restricting this growth is a fundamental law of astrophysics known as the Eddington limit. Formulated by Sir Arthur Eddington, this limit defines the absolute maximum luminosity a celestial body can achieve when there is a perfect hydrostatic balance between the inward force of gravity and the outward push of radiation, Pressure. When a black hole accretes matter, the infalling gas forms an accretion disk, spiraling inward at relativistic speeds. As the gas compresses, internal friction heats the material to millions of degrees, generating intense electromagnetic radiation, primarily in the form of high-energy X-rays and ultraviolet photons. If the central singularity feeds too rapidly, the sheer outward momentum of these emitted photons exerts a physical force on the surrounding electrons through Thomson scattering. This radiation pressure overpowers the inward gravitational pull, physically blowing away the surrounding gas and entirely starving the black hole of its fuel supply. Because of this self-regulating mechanism, a black hole's growth rate is strictly capped. To bypass the Eddington limit and explain the sheer mass of early universe quasars, astrophysicists hypothesized that the initial seeds must have started exponentially larger, a mechanism known as direct collapse, where an immense primordial gas cloud, prevented from fragmenting into stars by a background bath of ultraviolet radiation, implodes directly into a massive black hole of 10,000 to 100,000 solar masses. Yet even with direct collapse seeds, the growth rate required to match the James Webb data demands a mechanism that allows a black hole to gorge itself in flagrant violation of standard Eddington constraints. 16 years before the James Webb Space Telescope captured the first anomalous photons from the little red dots, the theoretical framework for circumventing this exact thermodynamic bottleneck had already been published. In July of 2008, astrophysicists Mitchell Beagelman, Elena Rossi, and Philip Armitage released a paper in the monthly notices of the Royal Astronomical Society titled Quasi-stars, accreting black holes inside massive envelopes. It was a purely theoretical exercise, driven not by observational anomalies which did not yet exist at those distances, but by the mathematical necessity of solving the supermassive black hole mass crisis. The team modeled a highly specific extreme scenario, a direct collapse black hole seed becoming deeply embedded within a colossal envelope of pristine hydrogen gas, an envelope weighing hundreds to thousands of times more than the singularity itself. In a standard active galactic nucleus, the black hole sits relatively naked at the center of a thin, highly organized accretion disk, its radiation propagating freely into the intergalactic medium. Beagelman's team fundamentally altered this geometry, asking what would happen if the accretion occurred inside a spherically symmetric, incredibly dense, and gravitationally bound gas cloud that completely encased the singularity. The physics that emerge from this configuration are profoundly counterintuitive and mathematically elegant. In this hybrid object, the Eddington limit still applies, but its application is radically displaced. The limit governs the radiation flux escaping through the outermost surface of the colossal hydrogen envelope, not the localized accretion boundary immediately surrounding the black hole. Because the outer envelope is so massive, possessing an immense gravitational binding energy, the central singularity can feed at super Eddington rates, gorging on the internal gas at a velocity that would normally obliterate a standard accretion disk. The horrific high-energy X-ray radiation generated by this hyperaccretion is entirely trapped. It cannot escape the dense interior. Instead, the X-ray photons undergo continuous Compton scattering, colliding with the densely packed electrons in the hydrogen envelope, losing energy with each collision and shifting to longer, softer wavelengths. This trapped radiation provides the immense internal pressure necessary to prevent the entire multi-million solar mass structure from collapsing inward under its own gravity. The black hole acts as the nuclear engine, and the surrounding envelope acts as the containment vessel, expanding and cooling as it absorbs the kinetic and thermal energy of the accretion process. Beagelman, Rossi, and Armitage rigorously calculated the thermodynamic properties of this theoretical structure, mapping its evolutionary trajectory over millions of years. They determined that as the central black hole grows, the massive amount of energy it injects into the envelope forces the outer layers to dramatically expand. As the envelope's volume increases, its surface temperature inevitably drops. However, stellar thermodynamics dictate a strict floor for this cooling process, analogous to the Hayashi track that governs the evolution of red giant and supergiant stars. The theorists predicted that the surface temperature of a quasi-star would stabilize at roughly 4,000 Kelvin. At this specific temperature, the opacity of the hydrogen gas, dominated by the formation of negative hydrogen ions, is perfectly tuned to trap exactly enough radiation to maintain hydrostatic equilibrium. If the temperature drops below this critical threshold, the negative hydrogen ions are depleted, the opacity of the envelope plummets, and the trapped radiation suddenly escapes into space. Without that internal radiation pressure holding the structure up, the outer layers of the envelope are violently expelled into the cosmos by the unleashed energy of the central singularity. The quasi-star phase is therefore highly transient, mathematically constrained to last only a few million to a few tens of millions of years before the stellar womb is annihilated. The extreme Balmer break observed in the spectra, a feature that initially tricked astronomers into assuming the presence of an incredibly mature, massive stellar population, is perfectly explained by the atmospheric dynamics of the quasi-star. In a normal galaxy, a Balmer break of this magnitude requires hundreds of millions of years of stellar evolution, as a massive population of A-type stars dominates the galactic spectrum. But in the quasi-star model, this sharp discontinuity at 364.6 nanometers is not produced by a vast collection of aging stars. Instead, it is generated by the sheer optical depth of the colossal hydrogen envelope itself. The neutral hydrogen in the outer layers of the envelope, sitting precisely at that 4,000 Kelvin equilibrium point, absorbs the ultraviolet radiation upwelling from the interior with brutal efficiency. The photons with wavelengths shorter than the Balmer limit possess exactly the requisite energy to ionize hydrogen from its second energy level, meaning they are completely devoured by the envelope before they can ever escape into space. This creates an artificial spectral cliff, a sudden vertical drop in the light curve that mimics an ancient galaxy, but is in reality the atmospheric signature of a single, monstrous, gas-shrouded singularity. For more than a decade, this paper languished in the academic literature, an elegant mathematical curiosity lacking any empirical verification. The instruments required to detect a quasi-star in the early universe simply did not exist. The required infrared sensitivity and spectroscopic resolution were decades away. But when the James Webb Space Telescope began returning the spectra of the little red dots, the data aligned with the 2008 theoretical predictions with a precision that bordered on the uncanny. The extreme compactness of the light sources, the characteristic deep redness, the nearly vertical Balmer break indicating dense, pristine hydrogen, the super-broadened emission lines caused by internal photon scattering rather than pure orbital velocity, and the complete absence of detectable X-ray emission. Crucially, the spectroscopic data revealed that the photospheric temperature of these objects held steady at exactly the 4,000 Kelvin threshold predicted by the Hayashi limit calculations in the Beegelman paper. Every anomalous data point that had systematically dismantled the starburst galaxy hypothesis and the standard active galactic nucleus model fit flawlessly into the physical parameters of a quasi-star. The universe had been operating exactly as the equations demanded. This precise alignment provides not just a structural identity for the little red dots, but a coherent chronological narrative for the evolution of the early cosmos. When astronomers map the distribution of these objects across different cosmic epochs, a stark demographic pattern emerges from the data. The little red dot population is highly concentrated in an extremely specific temporal window, appearing in vast numbers between roughly 500 million and 1.5 billion years after the Big Bang. In the subsequent cosmic eras, their numbers precipitously decline until they vanish entirely from the observational record. They do not slowly fade away. They undergo a violent phase transition. As the universe ages past the 1.5 billion year mark, the black holes inside these envelopes finally consume enough mass to push the photospheric temperature below the critical 4,000 Kelvin boundary. The envelopes detonate. The protective hydrogen cocoons are shredded by radiation pressure, and the objects transition into standard, violently luminous active galactic nuclei, completely altering the ionization state of the surrounding intergalactic medium. We are looking at a transient, highly volatile incubation period, a specific era in cosmic history where the fundamental rules of mass accumulation were temporarily rewritten. But if the little red dots are indeed the missing evolutionary link between theoretical direct collapse seeds and the supermassive black holes that anchor modern galaxies, their existence introduces a far more profound problem for the standard model of cosmology. By confirming that singularities can grow at super-Eddington rates inside massive primordial envelopes, the data forces us to confront the reality that the early universe was capable of organizing matter in ways that our foundational equations did not predict. raising the terrifying possibility that our timeline of galactic evolution is not merely incomplete, but fundamentally fractured. The standard cosmological framework, specifically the lambda-cold dark matter model, operates on a strict principle of hierarchical assembly. It dictates a bottom-up construction of the universe. In this paradigm, microscopic density fluctuations in the primordial plasma slowly gathered dark matter, which in turn created gravitational wells that pulled in baryonic matter. Small structures formed first. Dwarf galaxies emerged, collided, and merged over billions of years to construct the massive spiral and elliptical galaxies we observe in the local universe. Black holes were expected to follow this exact same regulated, incremental evolutionary track. They were supposed to grow alongside their host galaxies in a steady, proportional accretion process, governed by the same well-understood physics from the epoch of reionization to the present day. The little red dots completely dismantle this assumption. They suggest that the early universe contained a highly nonlinear, hyper-accelerated phase that our hierarchical models fundamentally fail to capture. We are observing a regime where black holes grew exponentially faster than theoretical limits permitted, sequestered inside massive envelopes that standard hydrodynamic simulations insisted should have been gravitationally unstable or blown apart by radiation pressure. This forces us to acknowledge that the foundational equations governing cosmic structure formation are missing a crucial variable, producing objects that refuse to fit cleanly into any of the taxonomic categories the astrophysical community has relied upon for generations. We have never been able to observe this phase before, because the instrumentation required to peer through the immense optical depths of the early cosmos simply did not exist. The James Webb Space Telescope has abruptly opened a sealed observational window, and the resulting influx of data is currently overwhelming the theoretical community. The scientific narrative is far from finished. In fact, it is being rewritten in real time. Papers analyzing the spectroscopic signatures of the little red dots are being submitted to astrophysical journals at a rate faster than the peer review process can comfortably accommodate. Hundreds of detailed analyses have appeared in just the last 24 months, creating a dynamic and highly volatile research environment. Every new deep-field observation Webb executes seems to yield more of these compact, luminous anomalies, transforming what was initially considered a statistical fluke into a fundamental structural component of the early universe. Yet, despite the sheer volume of incoming data, the black hole star hypothesis, while intellectually elegant, is not a finalized theory. It is a working model, and it is surrounded by a perimeter of severe, unresolved physical mysteries. The most pressing of these open questions concerns the initial formation mechanism of the hydrogen envelopes themselves. We do not currently possess a verified physical model explaining how such immense, concentrated volumes of pristine primordial gas could collapse into a hydrostatic envelope without first fragmenting into thousands of individual stellar cores. In the modern universe, gas clouds of this mass would rapidly cool through the emission of radiation by heavier elements, astronomical metals like carbon and oxygen, and shatter into standard stellar nurseries. The little red dots, however, exist in an epoch where these heavy elements were virtually non-existent. The thermodynamics of pure hydrogen and helium behave differently, potentially allowing for the direct collapse of massive envelopes, but the exact fluid dynamics and gravitational triggers required to initiate this process remain deeply speculative. Furthermore, we lack a precise mathematical understanding of what dictates the duration of the quasi-star phase. The theoretical models suggest a lifespan of a few million years before the internal radiation pressure overcomes the gravitational binding energy of the envelope, but the observational data shows a broader variance in the Balmer break strengths, implying that some of these objects might sustain their enclosed accretion for significantly longer, or perhaps shorter periods. We also do not know whether this evolutionary bottleneck is a universal requirement. Do all supermassive black holes, including the 4 million solar mass singularity at the center of our own Milky Way, originate from a black hole star phase? Or is this hyper-accelerated growth pathway exclusive to the absolute largest quasars that populate the high redshift universe? Could the specific environmental conditions, the extreme density and pristine chemical composition of the early cosmos, be the sole trigger, or could localized pockets of metal-free gas in later cosmic epochs occasionally replicate this phenomenon? At this exact moment in astrophysical research, the black hole star model stands as the leading explanation not because it has definitively answered all these questions, nor because every remaining puzzle has been neatly resolved. It has displaced the older, more established explanations purely through the rigorous application of Occam's razor. It accounts for a significantly larger percentage of the observational data, while requiring far fewer auxiliary assumptions. To make the starburst galaxy hypothesis work, astronomers had to invent physically impossible stellar densities and ignore the catastrophic deficit of far-infrared dust emission. To make the standard active galactic nucleus hypothesis work, they had to ignore the complete absence of X-ray luminosity and accept black hole-to-galaxy mass ratios that violated every known scaling relation. The black hole-star model requires no such mathematical contortions. It unifies the compactness, the extreme optical redness, the vertical Balmer break, the broadened hydrogen emission lines, and the missing X-rays into a single, cohesive physical mechanism. It is a testament to how scientific paradigms shift, not always through a single, undeniable proof, but through the gradual realization that the old frameworks can no longer bear the weight of new, higher-resolution data. The next decade of observations, utilizing even longer exposure times and more refined spectroscopic instruments, will inevitably sharpen this picture. It will constrain the variables, refine the thermodynamic models of the envelopes, and almost certainly introduce entirely new anomalies that our current theoretical framework has not yet anticipated. What the little red dots have accomplished, even before the final definitive answers are calculated, is a fundamental alteration of the story we tell about how the universe organized itself out of the primordial plasma. The standard model of cosmic evolution is not necessarily wrong, but it has been proven irrevocably incomplete. There is an entire chapter missing from the very beginning of the chronological record. We are discovering that the transition from the cosmic dark ages to the era of structured galaxies was not a gentle, linear accumulation of mass. It was punctuated by bizarre, extreme phenomena, objects that operated under extreme physical limits, growing central singularities at rates that defy standard accretion physics, all hidden behind impenetrable walls of glowing hydrogen. The little red dots are the first clear, unambiguous glimpse into the contents of that missing chapter. They represent a bridge between the microscopic quantum fluctuations of the Big Bang and the macroscopic, gravitationally bound supergalaxies that dominate the contemporary cosmos. And perhaps the most profound aspect of this entire scientific revolution is the realization that the theoretical architecture required to understand it was already in our possession. 16 years ago, long before the James Webb Space Telescope was anything more than a series of engineering blueprints and budgetary debates, three theoretical astrophysicists at the University of Colorado in Boulder sat down and wrote out the mathematical prediction for a class of objects that no human eye had ever seen and no existing telescope could ever detect. They calculated the hydrostatic equilibrium, the radiation pressure, the photospheric temperature limits, and the accretion dynamics of a black hole feeding inside a massive gaseous envelope. They published